Okay, good afternoon. Thank you for joining. First, I want to thank John Snow Labs for the invitation. It's an honor to be included among such an accomplished and talented group of practitioners of natural language processing in healthcare. And thank you for joining or watching later. I look forward to addressing any questions or comments that you may have. So a little bit about myself. I'm a data science lead at PresGainy. I have a sort of an interesting mixture of academic background. As an undergraduate, I studied physics, mathematics, and English. I was really interested in empirical sciences as practiced in physics, the formal science of mathematics, and really the subject matter of English. And I thought that those were all three really well represented in linguistics. So I went off to graduate school at the University of Texas at Austin for linguistics. And immediately after completing that program, I joined Narrative DX, where I was head of linguistics until our acquisition by PresGainy early last year. And I've been there ever since. At Narrative DX and then at PresGainy, we're very focused on experience data, both patient and other types of experience data. And of course, one sort of crucial component of analysis of language of that sort, typically from surveys and things like that, of course, is sentiment. And over the years, we've had a variety of approaches to categorizing sentiment, various machine learning algorithms and models, including custom neural networks, until our transition several years ago to a BERT-based transfer learning model. And our BERT-based model, as well as our earlier machine learning algorithms, have struggled with certain classes of phrases. So in particular, I want to point out a few examples that I'm hoping can be kind of a motivating theme throughout what follows about the kinds of things that have been problematic for BERT and our other approaches to sentiment. And these include sentiments or sentences of the sort 1, 2, and 3 here. Few nurses were very kind to us. It would be nice if the room was cleaned. And there should be friendly staff at reception, right? So for most speakers of English, comments of that sort are most likely to be classified as negative. What we found is that our BERT transfer model, trained on robust, naturally occurring annotated data, as well as other approaches, tend to classify constructions of this sort as positive, despite, like I said, robust training data. What I'd like to do is to try to motivate the augmentation of approaches using BERT and other machine learning algorithms or statistical context theoretic approaches to natural language processing with some findings from linguistic theory. And to do that, I'd really like to start with a very high-level, brief synopsis of what I see to be sort of the history of approaches to natural language processing, moving into more contemporary approaches, including deep learning and neural natural language processing, as everybody in this group is going to be familiar with, and then talk about how these can be augmented from linguistic theory, in particular, some of the ways that linguistic theory overlapped with some of the earlier approaches to natural language processing that have been less emphasized in more recent years. And then towards the very end, I can talk a little bit about how some of the things that we discuss here can be implemented in your own pipelines. Historically, prior to the sort of modern era of natural language processing, there was a certain amount of tension between symbolic and statistical approaches to, in particular, meaning for representations of natural language. Symbolic approaches oftentimes were inspired by formal logic and semantic theory, where they overlapped, and statistical approaches sort of had a different tack. So since this group is likely to be a little bit less familiar with symbolic approaches to meaning representations, I kind of want to show a couple of examples of what that might look like, all the while emphasizing that the details here aren't terribly important. I just kind of want to give a flavor for symbolic approaches to meaning representations. So here is a type lambda calculus at the lower level, and then sort of typed predicate logic at the top level of a representation of a sentence like, every doctor likes Dewey. So at the very top level, you see a predicate logic representation that uses this logical quantifier for any x. Doctor X is a doctor entails that X likes D, where D is the representation for Dewey. And these approaches represent syntactic structures, and usually the lower level elements, including the lexical items, every doctor likes Dewey, are abstracted from the more non-controversial logical representations as represented at the top level. And like I say, the details here aren't terribly important. I just kind of wanted to provide a flavor of symbolic approaches to meaning representations. Here's another example. Louis likes some skilled doctor, which the sentence as a whole can be represented using this existential quantifier. There exists some X such that X is skilled and X is a doctor, and Louis likes X. So this is a sort of straightforward predicate logic representation of a sentence of that sort. And then the lower level intermediate constituents and lexical items are usually represented as abstractions from that. And as I mentioned a couple of times, the details here aren't terribly important. What is important is what I suggested, which is that in these approaches, oftentimes the starting point is the logical truth conditions for an entire sentence. Usually using traditional approaches to logic and semantic theory, the logical truth conditions are determined for an entire sentence, and then the meaning of the individual elements are generalized using lambda abstraction or something like that from these. And crucially, these approaches tend to respect syntactic structure, and they are a good way of representing semantic compositionality. So they preserve meaning interactions between elements in whatever utterance they're representing. However, many content words, so nouns, adjectives, and some of the more common verbs, are often left unanalyzed in approaches of this sort. And even the so-called logical words, those which provide some sort of sublexical representations, sometimes they become very complex in these kinds of representations. And a lot of times you'll end up with exotic operators and primitives that are less easy to deal with. Here's another example of a symbolic approach to meaning. Here's event semantic representations of sentences like John forced Bill to dance, John had Bill dance, and John got Bill to dance. And already you see, even at the top levels sentence representation with these event semantics, you end up with some interesting primitives and operators that are not necessarily going to be, they're not going to be immediately apparent, and they tend to be computationally less tractable for a lot of purposes. And then, of course, when you abstract away from the senses and get this sublexical meaning, here are some representations for the so-called paraphrastic causative verbs in English. These can quickly become very complex and difficult to deal with. And again, this is event semantics using also predicate logic and lambda abstraction, but the details here aren't terribly important so much as the approach. And I want to contrast that symbolic approach to meaning representations with these statistical or context theoretic approaches, which often sort of tackle the problem from the opposite direction. So they often start with lexical items themselves, and then based on the co-occurrence of lexical items in some large corpus or some document, you can embed these in a vector space, and then interesting semantic properties can sometimes be discovered in these vector spaces. So here are some examples where based on co-occurrences in some documents, words like king, queen, man, and woman, their position and orientation in a vector space of co-occurrence seems to suggest meaning distinctions such as male, female in terms of their related orientation. Likewise, sometimes verb tense can be represented or discovered in these vector spaces. So past tense verbs like walked or swam seem to have the same relationship to their participles or their progressive aspect versions, walking or swimming. And then sometimes even in large enough corpora, you can get interesting representations of relationships like country and their capital. So here's some examples of just orientation based on co-occurrence in a vector space, gives you interesting lexically semantic properties. Some amount of compositionality, so the interactions of various meanings can be represented. It's possible to represent some of these in embeddings of this sort, in vector space embeddings, but that's not usually the focus. nor is it the strength of approaches of this sort. One thing you can do is represented here. If you have these vectors, co-occurrence vectors, you can do simple vector addition to get some compositional representation. So in this case, we have these noun, and then it becomes a modified noun, like good experience versus bad experience. You can represent those higher level constituents as just an addition of the items, vector addition in this case. But like I say, that's not the approach that's emphasized in these context theoretic models. Okay, so that's very quick and hand wavy, and I'll be even quicker and more hand wavy in my discussion about deep learning and neural natural language processing. This is the more contemporary approaches, and most folks in this group are going to be most familiar with this. In particular, for natural language processing, of course, a real revolution happened with the advent of BERT, which we're all familiar with. This is the model from Google that was trained on a huge corpus of unannotated data that was manipulated in a way that allowed for training. And then here's an example. So there were a couple of tasks that BERT pre-training focused on. A bunch of data from the internet was used, and then lexical items in that data were masked randomly. And then one of the tasks was prediction of those masked lexical items. Another task had to do with judging whether one sentence was likely to follow another based on training of masked entire sentences. But the important thing here is that this model was able to be pre-trained on a huge amount of data, and then the process of transfer learning, where you could take this pre-trained model, train it on your own annotated data for your natural language processing task of preference, and it would be able to sort of shatter benchmarks, and it did that very quickly. So this represented a real revolution in NLP. So for example, if you're trying to get a BERT-based transfer model to predict sentiment, which is the focus of this discussion, you could take this pre-trained model and then train it on your own annotated data for sentiment, and it would perform better than most other models. Again, the input representation is still these sort of token embeddings. So just the lexical items themselves, some amount of sublexical embedding, or some amount of sublexical representation. In this case, you have my dog is cute, he likes playing, and playing is represented as the lemma play plus this morpheme, the progressive morpheme. These token embeddings, along with some segments and information about some phrase level, clause level stuff like separators between clauses, and then position embeddings. So a way to kind of extract how words co-occur. Again, this is something that most people in this group are going to be very familiar with. Like I say, these approaches shattered benchmarks pretty quickly. And so one of the questions that a lot of folks had who were interested in this was, what exactly is BERT learning when it's doing these tasks with all this data? And so an important paper that looked at that exactly is this paper out of Stanford and Facebook, which was just an analysis of attention heads for BERT predictions. And what they found is that BERT seems to kind of be learning linguistic theory at some level. In particular, it seems to be learning certain syntactic relationships implicitly. So for example, one discovery was that direct objects tend to attend very heavily to their verbs. Noun modifiers attend to the nouns that they're modifying. Possessive pronouns attend to the head of the corresponding noun phrase, so usually the head noun. Passive auxiliary verbs attend to the verb that modifies, so this market has been very badly damaged. The auxiliary been attends heavily to damaged. Prepositions attend to their object. Prices of bonds of would attend to the bonds, and so on and so forth. So the generalizations that BERT in all this data seem to be reconstructing and implicitly learning things related to syntactic theory. And this is not unexpected, it's not undesirable. In fact, it's exactly what you would expect if these models are to be effective, right? If the findings of linguistic theory are valid, and these models are learning well, they would implicitly be learning some of these scientific generalizations about the structure of language, which is not unexpected. One thing that occurs to me, though, when you look at this type of data or this type of attention behavior, is that there may be a certain amount of reinventing the wheel, right? So you can imagine an analogy of feeding a sophisticated neural net a lot of information about planetary positions, and then having it predict subsequent positions based on a lot of training data. And then when you look at the behavior, if you try to open up the black box in those cases, you're likely to discover that at some level it's recreating Kepler's laws or Newtonian mechanics or something like that, as it should. But what's interesting is that in practical cases, if you're training up a model like BERT, some of the high-level sort of scientific generalizations about, in this case, the structure of language, are likely to be well represented in your training data. But equally robust findings from science may be sparse in natural language training data sets and may not be well represented. And that's really what I wanted to focus on, and what follows is a discussion about how certain findings from linguistic theory can be used to augment approaches that rely on robust training data when the training data may not be available. So just as a reminder, I wanted to kind of redirect your attention to these problem sentences that we mentioned earlier. Few nurses were very kind to us. It would be nice if the room was cleaned, and there should be friendly staff at reception. So like I say, in all of these cases, most speakers of English are going to very quickly judge these to be negative. And in fact, they're so sort of straightforwardly negative that a lot of times if you're doing some production level NLP, and you mispredict these, and you predict them as positive, which is what we found our models tend to do, it's going to be an eroder of confidence. You're going to discover that people are going to lose faith in your ability to do effective natural language processing. So it's very incumbent upon production level NLP to get these types of sentiment predictions right. And so my question is, what can linguistic theory, if anything, tell us about examples like these, and in particular, how to think about the sentiment that's represented in sentences like these? Okay, so when it comes to the interaction of certain operators, and I'll be more specific about what I mean there, and things like sentiment, the area of linguistics that's most likely to be useful is semantic theory. And so if you were to crack open a semantics textbook, or really formal logic more generally, one of the fundamental topics that you're going to discover right away is that of inference, right? Which is just the question of what can someone assume to be true or false based on some utterance or proposition, right? What follows from what? And in natural language, there are several varieties of inference that people tend to identify. And the most salient and the least controversial of these include entailments, implicatures, and presuppositions. And it turns out that these types of inference patterns end up being very useful for understanding and correcting how certain types of linguistic structures interact with sentiment. And so I want to go into a little bit of very quick detail about these and how certain findings and generalizations can be used to improve predictions for sentiment in your pipeline models. So entailments are the bread and butter of inference. These are the cases where a sentence immediately follows another sentence, right? So a sentence A entails a sentence B if and only if every situation that makes A true also makes B true. So a good example of this is the case where if you have a sentence like John has a surgeon, as long as all the words are being used in canonical, straightforward ways here, that's going to automatically entail that John has a doctor, right? The utterance of John has a surgeon is true if and only if John has a doctor is true. And there are a number of important properties of entailments. They're non-cancelable, right? So it's semantically infelicitous or logically incongruent to say something like John has a surgeon, but he doesn't have a doctor. Usually if somebody hears an utterance of that sort and tries to make sense of it, there's going to be some amount of coercion. The assumption is going to be that people are using some of these words in non-canonical or deviant types of ways. Typically, John has a surgeon, but he doesn't have a doctor is not coherent. And they're not preserved under negation, and some various other operators that I'll talk about momentarily. So John doesn't have a surgeon no longer entails that John has a doctor. It may be true that John has a doctor, even if John doesn't have a surgeon is true. He may have a different type of specialist, but it no longer automatically follows under negation. So if I say John doesn't have a surgeon, or it's not the case that John has a surgeon, you can no longer make the inference that he is a doctor. The case of implicature, I include here sort of for completeness. It's a different type of inference. It really has to do in the domain of pragmatics rather than semantics proper, I would say. But it has to do with an utterance in some context and the types of conclusions that a rational agent is likely to make. So kind of a quick definition is that an utterance A will implicate a proposition P if and only if the use of A in some context typically implies P. So for example, if I say John went to a specialist for a checkup, most rational speakers in most contexts are going to conclude that John has a doctor. However, these are cancelable, and there may be contexts for which those conclusions don't follow. So John went to a specialist for a checkup. He doesn't have a doctor, but he has a very good mechanic. This is sort of allowed in most contexts where you would say, oh, the specialist is an auto specialist, right? And the checkup is for a vehicle of some sort. So that's a feature of implicatures. They're also less predictable in terms of their behavior under negation and various other operators. And implicatures, like I say, are really included here for completeness about inferencing patterns. What I'm most interested in and what ends up being most crucial for the interaction with sentiment are entailments, these right here, and presuppositions, right? So presuppositions are when a certain proposition or sentence must be true for a sentence to have any truth value at all, to either be true or false. So an example of this is if I utter, John's doctor is skilled, it's going to follow that John has a doctor. But if I negate that, it's still going to follow, right? So John has a doctor has to be true for either John's doctor is skilled to be true, or it's not the case that John's doctor is skilled is true, right? Like entailments, these are non-cancelable. So John's doctor is skilled, but he doesn't have a doctor is even harder to imagine. But like I mentioned, they're preserved under negation and some other operators that I'll talk about momentarily. So John's doctor is not skilled. It still follows from that John has a doctor. So that's this distinction between entailments and presuppositions. So negation, so one thing you'll discover if you sort of dive into classical formal semantics is that there's this discussion of behavior of presuppositions with certain types of operators that are oftentimes referred to as plugs, filters, and holes. So negation is an example of a hole for a presupposition, and it's called that because presupposed meaning seems to pass right through it. So you can negate a sentence that presupposes something, but it's still going to presuppose it. There are also plugs for presupposition, which block meaning, or the presupposition no longer will hold. These typically act as plugs for entailments. One sort of clear example of that is this belief predicate, right? So you can say, Mary believes that John's doctor is skilled, but John doesn't have a doctor. So that's still felicitous. So it seems to have blocked the presupposition in the early clause. Just to kind of round out these types of things, I'll talk very briefly about filters. This is an interesting case where presupposed meaning seems to be filtered out via interaction. This is going to sound complicated, but it's not as complicated as it looks. Via interaction with a proposition for which the same meaning is entailed. So a good example of that kind of makes it clear is that if I say, if John has a doctor, then John's doctor is skilled. In that case, it no longer presupposes that John has a doctor because the antecedent clause entails that John has a doctor. So the presupposed meaning in the consequent clause is now filtered out. Okay, so that's one thing that you'll find if you start to look at these different types of inference patterns. In addition to negation, there are other operators that act as holes for presuppositions, but that still continue to block entailed content. These include questions like, is John's doctor skilled? Modal verbs, John's doctor might be skilled, or it could be the case that John's doctor is skilled. If clauses and various other types of counterfactuals, like if John's doctor were skilled, he'd still be alive. In what follows, I want to focus on negation and modal verbs, but many of the observations that that we make about negation and modal verbs and their interaction with sentiment in particular are more broadly applicable to other types of operators. So when it comes to inference, it turns out that these different inferences are directly applicable to sentiment. So one of the canonical carriers of sentiment in natural language are adjectives, right? And it turns out that depending on how the adjective appears in the sentence syntactically, it may be presupposed or entailed by that sentence, right? So, for example, sentiment-carrying adjectives in the predicate position, as in 7, the nurses were nice, and we assume here that nice carries positive sentiment, are entailed, whereas attributive adjectives in their sentiment are presupposed. So the nurses were nice, the fact that the nurses were nice and any sentiment associated with nice is an entailment in 7. The nice nurses were tall. All the information about nice in 8 are a presupposition, right? So the meaning of the attributive adjective and any sentiment that is associated with it are presupposed in examples like 8. Okay. All right. So I want to kind of transition from there and talk about these interactions with some of these operators with sentiment, and how you can augment statistical analyses with these more sparse structural determinants of meaning, and use linguistic theory as a way to augment your pipelines to better make predictions by leveraging some of these sparser types of operators. So an important point is that negation in general, and any kind of sentiment that's in part of an entailed predicate or an entailed carrier of sentiment tends to reverse the polarity of that sentiment. This is sort of straightforward, right? So if you say nurses were nice, that is typically going to be judged as positive. If you negate that and say nurses were not nice, or it's not the case that nurses were nice, that typically reverses the polarity of the sentiment, and now it's negative, right? You can compare that to the attributive adjective case where the nice nurses were tall. That's usually going to be judged as positive or neutral. You can negate that, that is positive or neutral based on the attributive adjective nice, and then you can negate that and the same sentiment holds. So this is in the entailed position. So in most of your statistical models, including BERT, if you have robust enough training data, most negation and its effect on sentiment is going to be learned pretty easily by sophisticated modern versions of this. But negation as it occurs in natural language is not just this words like not and the contraction, things like that. It turns out that there's a lot of sort of covert or subtle types of negators that have similar effects on sentiment, but are less likely to be learned by your models. And one thing that's interesting for negation discovery in English and other languages are these class of words called negative polarity items. So in English and some other languages, there are certain types of words that only occur grammatically in the scope of a negator, right? One good example of that is this word any. I should say just from the very beginning that there's a certain amount of polysemy with any. There is a different type of any. That's the so-called free choice any. These are the cases where you could say the teacher could give any student a book. And in those cases, it doesn't necessarily have to be under the scope of a negator. But in most uses, it's perfectly natural to say nurses didn't give us any attention, but it suddenly becomes ungrammatical to say nurses gave us any attention, right? So these are the cases where the negators are likely to be learned by BERT, but there's subtler types of negators in English. Another example is no nurses gave us any attention is fine. Some nurses gave us any attention is not fine. So you see that these quantifiers, these determiner quantifiers, now can act as negators too. This is also likely to be learned by any robust training set, but there are subtler cases, right? So here's a good example where you would need a lot of data and a lot of attention to very subtle distinctions to gather that few, as in 14a, few nurses gave us any attention is a negator, whereas if you say a few nurses gave us any attention, that's no longer a negator. and the effects on sentiment are as predicted, right? So few nurses were very nice is negative. A few nurses were very nice is typically positive. So even these subtle covert negators have the predicted effect on sentiment, but they may be very subtle in natural training data, which is the reason why the problem sentences that we discussed at the top tend to be problem sentences in the first place. Modal verbs are similar. So the nurses were nice versus the nurses should be nice. Signage was helpful versus the signage would be helpful. These are operators that also tend to reverse sentiment, but oftentimes are very sparse in natural language. So here's an example from the British National Corpus. These are frequencies for a variety of modal verbs per million words. You see that for most modal words in English, they're somewhere in the domain of a few hundred to a couple thousand, and not necessarily likely to be learned in a practical training data set, which is the reason why we had problems with the problem sentences that we mentioned. Very quickly, just to wrap up, I know we're about time here. I'll say that you can discover covert and subtle negations by looking through large enough corpora for various negative polarity items. And there are a number of negative polarity items in English. These can be found in a number of resources. And then the modal verbs are just a closed inventory. They're a closed class of verbs. So you can basically do some sort of preemption of your prediction models or post-processing by looking at these negative polarity items and these modals. You can do a string match for regular expressions. Here's an example of that. But I think a more productive approach is to look at the output of the part of speech tags for a more sophisticated parser. So this is an example of the output of Spacey. It's very good at recognizing modals such as could and the staff could treat me better. And it does this for a variety of cases. These are some other examples that aren't as clear, but I'll just jump past that. And as far as resources for learning more about linguistic theory, these are some great textbooks about linguistic fundamentals for NLP. I recommend these. Here's a link to a free, although it's not nearly as detailed resource for that. And in general, please contact me if you have any questions or if there's anything else you'd like to discuss. And I thank you for your attention.